Hardware to Save a Planet explores the technical innovations that are giving us hope in the fight against climate change. Each episode focuses on a specific climate challenge and explores an emerging physical technology solution with the person bringing it into reality. I'm your host, Dylan Garrett. Hello and welcome to Hardware to Save a Planet. We get to talk with two guests today from Modern Electron, Mankin, CTO and co-founder, and Mothusi Pahl, Vice President of Business Development. We'll be talking about Modern Electron's technology, which decarbonizes natural gas use by converting gas to clean hydrogen at the point of use without CO2 emissions. This is important because hydrogen can be used instead of burning fossil fuels in some of the toughest applications to decarbonize, like industrial process heat production for things like steel manufacturing and steam generation. Just that, as an example, just industrial heat generation is responsible for something like 20% of global CO2 emissions. So it's a really important problem to solve. By leveraging our existing natural gas infrastructure, Modern Electron's solution can be deployed without waiting for new hydrogen distribution infrastructure to be developed. So this is really cool stuff, and I'm excited to learn more about it. Max and Mothusi, it's great to have you. Thank you for joining us.
Thanks, Dylan. Yeah, I really appreciate the opportunity. Great to be here.
So I'd love to hear more about your backgrounds and your paths to working on climate and any kind of major inspirations along the way. Max, let's start with you.
I've always been really excited about science and technology as it relates to clean energy. And actually, I remember even as far back as when I was a kid growing up, I was encouraging my parents to get a wind turbine in the backyard. And at the time, it was way too expensive, and it's still pretty expensive for homeowners to do this. So I ended up building my own, actually out of a dishwasher motor. And it only made about 10 watts. So it really did not help them with their power bill. And I ended up kind of giving up because I didn't have the right electronics as a kid and quickly went back to like teenage boy things like potato cannons and catapults and stuff. But that passion kind of remained. And I did my undergrad at Brown in physical chemistry and materials engineering and worked on a catalyst for fuel cells. And then got my PhD at Harvard working on projects for improving solar radiation collection and energy efficiency. And it was during that time that I learned a lot more about the scope of climate change and the big scale of the problem as well as the opportunity. So part of that actually came from watching the 2008 cleantech bubble implode, mostly from the sidelines. And one lesson I took from that as well was that the technology, good technology alone isn't enough. The business also has to be viable. And so at that time, I started educating myself on entrepreneurship and business and what it takes to actually start and scale a clean tech business, and ultimately got involved as an entrepreneur in residence at a deep tech incubator here in Seattle and spun Modern Electron out of that incubator.
That's got to be one of the better childhood inspiration stories I've heard. That's amazing. How about you, Mothusi? Any DIY energy generation in the backyard growing up?
No DIY generation, but I grew up in a house. My dad was an Eagle Scout, so we spent a lot of time outside. But Friday evenings were always spent watching Wall Street Week with Louis Rukeyser. So no one was surprised when my first job out of school was as a whitewater river guide. But my river clients were always surprised to find that their river guide moonlighted as an investment banker in the Bay Area during the work week. So I ended up back at grad school at Yale, got recruited by Cummins, was general manager of their power generation business in Southern Africa. And it was there building power plants for large industrial mining and oil and gas customers that I was really struck by the challenges and the complexities and really the energy demands of heavy industry. And that was where I started pushing into waste heat recovery and combined heat and power and decarbonization. And that's where I spent the last 15 years. It's really been focused on energy and heavy industry. And the big signposts along my technology path were with Alphabet Energy, and then co-founding a startup and taking it through StartX at Stanford. And ultimately, that's how I arrived at Modern Electron.
What was the startup?
Undaka. We were doing data management and IoT integration for oil field operations. It was all efficiency improvement and stopping trucks from driving out to field locations and reducing emissions associated with truck traffic.
Very cool. So you're both really deep in the space, it sounds like, and that brings us to Modern Electron. Max, I'd love to just hear from your perspective a little more about the problem you're solving. And we haven't done a show focused on hydrogen before, but why is this important?
So Modern Electron is decarbonizing tough to electrify sectors like industrial process heat and building heat, and most importantly, doing it without requiring new infrastructure to be built. There are two reasons why this really matters. First is around carbon emissions. Heat is 50% of final energy demand and accounts for about 1/3 of carbon emissions in the US. And much of that comes directly from natural gas combustion to both heat spaces as well as to heat processes like making steel, cement, paper, and actually even beer and alcohol are often made by burning gas for heat. And the US EIA actually forecasts that even in about 30 years, in 2050, we'll be using approximately the same amount of natural gas that we use now. And the situation is similar for the rest of the world. So we expect these CO2 emissions to continue. So if we can find ways to actually lower the CO2 emissions from use of natural gas, that's an enormous opportunity. Second is the infrastructure piece. We have something like 3 million miles of natural gas grid in the US alone. And it took us about the better part of a century to build out that natural gas distribution grid. Hydrogen is a really good opportunity and a good alternative to natural gas. It burns hot and it burns clean without CO2, but it has a couple of disadvantages. One is lower volumetric energy density than natural gas. And it's also really tough to transport. You can't really ship it around at high concentration in today's gas grid. And it's hard to compress into tanks. And so replacing these 3 million miles of natural gas grid with a clean hydrogen grid would take decades and cost us trillions of dollars. So if we can use today's infrastructure and decarbonize natural gas use at the same time, that's a win-win, both for decarbonization and being able to continue our industrial processes as we currently do.
Do you think we'll get to a place where we have hydrogen infrastructure at some point in the future?
I have no idea. I think there's a big opportunity, and a lot of gas utilities are talking a lot about it. I do think long distance transmission pipelines are a possibility on the horizon, although they don't really exist yet. The bigger challenge, I think, would be replacing all of the local distribution pipes. There are more miles of those actually than the long distance transmission lines. The challenge in replacing pipes is kind of twofold. One, you have the cost. It costs order of magnitude $1 million a mile. So 3 million miles, this isn't a cheap problem to solve. And second, it's a hassle, right? You're digging up streets, you're digging through people's backyards, you have to run a pipeline, and we all know how challenging that is in today's political and regulatory environment. And so I think it has some real challenges, but people are talking about it. So we're eager to see what happens.
Yeah, it's interesting. I keep coming across these companies like Modern Electron that recognize like we need a solution now, and we need to work within the constraints of today's infrastructure and all of that. And yeah, it sounds like that's what you're optimizing for, which makes a lot of sense.
Yeah. And to your point about a solution now, CO2 and methane stick around in the atmosphere for a long time. And so the warming that they do is not an instantaneous thing, right? You have to integrate that warming over the lifetime of that molecule in the atmosphere, which is order of magnitude decades to 100 years. And so if we can start decarbonizing now, that decarbonizing now, in other words, is potentially more valuable than decarbonizing later.
Maybe this is a naive question, but what is so hard about electrifying heat? I've got a heat pump at my house that heats, but I think we're talking about much higher temperatures. And yeah, can you explain that a little bit?
A couple things. So one is that electricity is typically 3 to 5 times more expensive than natural gas on a per energy basis. And so first of all, if you convert, even assuming 100% efficiency, if you converted your gas heating to electric heating, you're going to pay more on your heating bill. The second thing is that most industrial process heat is hot. It's over 100 Celsius. And so notable examples, right, are 300 to 400 Celsius steam heat for processing paper and pulp, like all the paper you get at Staples is made this way, or over 1,000 Celsius for processing things like steel and copper. And that is just very, very challenging, not to mention expensive to electrify. And the high grade heat is not something that a heat pump will be able to do in the near term future.
So that sets up the problem really well. Maybe Mothusi, can you describe the solution and how it addresses those things?
Absolutely. To the point that Max was making earlier, that one of the challenges with decarbonizing fuels and decarbonizing heat is, how do you get the energy where you need it? And also the rate limiting step of, as an industrial operator, if you have equipment in the ground and it has 15, 20 years of useful life left, like, are you really going to rip it out to put something new in that you don't really understand yet? Or put something new in that's going to completely change your process? So the approach and value proposition on the Modern Electron side is really around distributed decarbonization of natural gas, that we can place a box next to a gas meter at a factory, literally strip carbon out of that natural gas and deliver clean hydrogen to industrial customers, to commercial customers. And we can do that without having to materially impact the existing infrastructure on the ground. And we can do that at really low CI score. So what we're getting to is the point of very quickly being able to deliver the functionality and the convenience of hydrogen without the kind of legacy burden of hydrogen, which has been central generation of hydrogen and then transporting over the road and then storing on location in a tank. Like, there's just lots of logistical issues along that value chain that have been a real rate limiting step in introducing hydrogen into the marketplace. So by using Modern Electron technology on the location of the end user's application, we're really helping accelerate the end user's path to decarbonization and skipping a lot of the rate limiting steps that have slowed hydrogen down historically.
Yeah, as you're describing it, I'm kind of thinking of it as so natural gas is CH4, or I'm no chemist, but basically you're using the gas as a delivery mechanism for hydrogen atoms, right? It's one carbon and four hydrogens.
That is exactly.
That's right. That's right. Yeah. So natural gas is mostly methane, which is CH4. And it turns out that carbon atom at the center of that methane molecule is one of the best transport agents for four hydrogen atoms. So there's an enormous opportunity here to use other gases like methane and ammonia as transport agents for the hydrogen and completely circumvent hydrogen transportation and compression challenge that Mothusi mentioned.
Just to be clear, Dylan, our argument is not that green hydrogen or hydrogen that's driven by electrolysis or produced by electrolysis is a bad approach. It's not that at all. We think that's a great approach and is going to increase importance over time. But the rate limiting steps around hydrogen today are the exact same rate limiting steps around electrolysis. So that it's got to be cost effective. It's got to be able to get it to site reliably, and it has to be economic. And we think that natural gas as a carrier of those hydrogen atoms ticks all those boxes.
Right. If you were to put a clean hydrogen electrolysis production system at every factory, I guess the story here is that that's not economically viable.
Today, it is not, for a number of different reasons. One of those, Max mentioned earlier, the cost of electricity versus the cost of natural gas. In a place like California, where we barely have enough electricity as it is, like, where are you going to get all the power to drive all that electrolysis? And two, you need to be able to produce enough of it in advance to put into a tank to store for the person to use when they need it. So one of the really beautiful things about our existing natural gas infrastructure nationally is it's really like a big capacitor. It's a battery that's holding fuel for when you need it. So we're really leveraging and building off of functionality that's already in our existing natural gas infrastructure.
So let's talk about the box. You mentioned a box that does this. It's taking natural gas in, you get hydrogen out. What's going on in there?
So we have a process called methane pyrolysis. And methane pyrolysis is basically when you heat up natural gas a whole lot and you split that carbon and hydrogen bond. So for every atom of CH4 that goes in, you get 2 molecules of H2 and 1 atom of C coming out. The H2 can then be used for whatever you want. On-site process heat. You can run it through a fuel cell or an engine to generate power. You can use it in a chemical process. And then the carbon comes out basically like fluffy black powdered sugar. So this is called carbon black. And it's widely used in things like making tires, making asphalt, and roofing shingles, and so on. And actually, that's what makes like tires and roofing shingles black, is the carbon black in there.
Pyrolysis, just to explain that, can you describe how that process works?
So pyrolysis is basically when you get the methane molecule really hot. And so the simplest way to think about this is, let's say you have a really hot tube. And so you flow your natural gas through that really hot tube. The methane in that natural gas will just split. That thermal energy from the heat over 1,000 degrees Celsius is enough to actually just perform this chemical reaction and split the natural gas into carbon and hydrogen. The real challenge that we're addressing is, A, how do you do this efficiently and cost effectively, right? Getting that heat in, getting it hot, getting the gas to flow through efficiently. That's all very challenging. And second is, how do you get the carbon out? That's been one of the big fun technical challenges to solve. And we have some really cool solutions.
Maybe we'll get into the technology a little bit later. Before we do that, Mothusi, I'd love to hear more about the business model. And just maybe we can start with kind of, who are your customers and what are you selling to them? Are you selling equipment or a service of some kind?
So all of our customers today, you can draw a straight line from natural gas. They are either commercial or industrial in nature, or maybe running high density residential buildings, but they have large process heat or space heating or water heating demands. That's kind of broadly speaking category one. Category two are gas utilities with major stakeholder pressures to decarbonize and under major pressure to reduce their Scope 3 emissions.
Got it. So they would be within their existing kind of natural gas infrastructure and distribution. They would be placing your systems in places where they would then sell hydrogen to their customers.
Absolutely. So I mentioned earlier that our boxes are typically deployed at the meter, at a customer location. That can be behind the meter, so between the meter and the customer site, or it can be in front of the meter where the utility is literally delivering the gas. So one of our questions is, in terms of a preferred operating model from a utility, like, do they want to bundle pyrolysis unit with a meter? Do they want to be involved in the deployment of hardware on a customer site to help the end user decarbonize? Or do the utility want to be at arm's length? And I think the jury's still out there. But one of the interesting things that we're finding is, in my career, I've never seen utilities move as quickly as they are today in trying to understand for themselves what this future state of hydrogen looks like. So we're working on both sides of the meter. We're working with gas utilities and we're working with large consumers of natural gas.
Mm-hmm. And in both cases, you're selling them a piece of equipment and then they're owning and maintaining it.
Good question. So more often than not, what we see if you run a factory, very few people on a factory want to be responsible for running another piece of equipment. Most of the folks in a factory with a heating load just want to buy natural gas. They want to buy fuel. So in those instances, we think the longer term proposition is probably BTUs as a service, selling fuel for heat. On the utility side, the primary interest there is, utilities are unique in structure because they have like a legal mandate to be able to pass the cost of their infrastructure onto customers. So utilities really like buying hardware because they can fold that into their rate base. So we think one business model associated with utilities is our selling the hardware and then an ongoing service contract. But in the factory space, more often than not, it doesn't seem like they want to buy. They want to decarbonize, but they don't want to buy the hardware. So in a factory, they just want the hydrogen. The utility wants the hardware so they can pack it in the rate base.
And can you unpack that purchasing decision a little bit more on the factory side? So it sounds like they're motivated to decarbonize, and maybe that's aligned with, is that regulatory pressure?
So there's no question that they're motivated to decarbonize, but they are also motivated to manage their costs. They have CapEx that they got to keep in check, and they've got OpEx they got to keep in check. And in a space where electricity prices are constantly increasing, the idea of maintaining non-electric heat source and a low carbon heat source is of high value. And if the opportunity cost is a question of, do I swap out, if I need to reduce my carbon footprint Am I going to swap out the furnace or the boiler that I have today? Or am I going to try to keep what I have today and reduce the carbon footprint associated with the fuel that I'm putting into that? Especially on the front end, if I'm trying to get visibility of what this future state of decarbonization of my industry looks like.
I assume at some point too, they're looking at dollars per BTU or something like that. And how would this compare to just natural gas?
Yeah, so in terms of unit economics, the easiest way to think about what we're doing is the conversion of natural gas into hydrogen we're a ratio roughly of about 2-to-1. So for us to decarbonize your fuel source, you're going to put twice as much natural gas in to get carbon-free fuel out. And that's really the life cycle cost that we go through with our clients. At the end of the day, if you're not interested in decarbonization, there's no reason for you to do this. But if you are interested in decarbonization, then the question is, how much do my decarbonization opportunities cost? And what are the ancillary costs of me swapping out equipment? What are the ancillary costs of me having to rejigger my business because now I have a new process in place? And those are really high value conversations that we have with our customers on their front end, is really understanding how they're forecasting natural gas prices, because that's the primary input in their cost model.
Mm-hmm. So you're producing, or the system produces carbon black. I know that's valuable, like Max mentioned, for a number of different uses. Is that something that your customers could monetize, or that you would monetize in some way? What happens with that?
That is a great question. So our economic model is not contingent upon us realizing revenue in the carbon black department. So if we can find customers, and there's no reason to suggest that we can't, if we can secure offtake agreements for that carbon black, that ends up being an economic benefit for our end users. But our technology did not originate with optimization, or we were optimizing for hydrogen production, not optimizing for carbon black production. So on the front end, our expectation is whether this can end up as a soil amendment or can end up in asphalt on a road, we're pretty agnostic on where it ends up. We know that it is a high value output, and over the coming months, we expect to have some pretty significant releases around commercial progress just on the carbon black side. But in the interim, carbon black is really easy to sequester. It's a lot easier than CO2. You don't have to pressurize it. You don't have to gather it. You don't have to put it in a pipeline, and you don't have to inject it in the ground. Really, you can put it in the ground and put dirt on top of it, and it is officially sequestered.
Max, let's talk about the technology a little bit more. So you started talking about pyrolysis, and I guess I'd love to hear what about this has required innovation. And this is a hardware kind of focused show. So anything you can share about kind of the challenges on the hardware side would be really interesting to hear about.
This is a challenging system to build. And as we mentioned earlier, methane pyrolysis operates really hot. So it's about 1,000 degrees Celsius. And hydrogen and methane and all these things, they're potentially challenging gases to handle. And so a lot of the challenge has really been around two elements. One is, how do you get this thing hot and reliable such that you can efficiently split the methane or split the natural gas into carbon and hydrogen without the thing breaking, right? And there aren't that many commercial systems in the world that operate at these kinds of temperatures. So we've had to go through a lot of iterations to make sure that we have, for instance, our high temperature joints worked out correctly. And our materials selection is really important to make sure we pick the right materials and the qualified materials to make sure that, hey, this thing's going to be reliable and work consistently out in the world. The second challenge, as we kind of hinted at earlier, is how do you actually get the carbon out? So carbon black is like, it's sticky and it's fluffy. And you can think of like if you mixed a little bit of glue into like powdered sugar and mixed it up, it would feel sort of like that when it's hot and like coming out of the system when it's freshly generated. And so it grows in a lot of forms. And if you don't handle it right, it ends up actually clogging filters and pipes, and it'll get in pumps and degrade the seals and cause all kinds of problems. So a lot of our work so far has actually been on developing some amazing carbon handling designs that actually continuously move the carbon out of the pyrolysis system. So out of that tube, we talked about the hot tube where the methane is split into hydrogen and carbon. And so this system is basically continuously moving the carbon out of that system and into a collection area for reuse or disposal.
Can you talk about what that looks like? Do you have, I don't know, I'm picturing like an auger and some sort of filter system. What does it look like?
Yeah, so it's a version of an auger that's specifically designed to operate in this super high temperature environment with a specially designed seal to contain the hydrogen. A lot of what we tapped here was around high temperature material selection. So making sure that this thing, A, is properly thermally insulated, and B, is made out of the right materials so that it works reliably. And then ultimately, what we use are kind of downstream from that are kind of the standard carbon black handling systems. So think like cyclones and filters, as you said, and things like dropout boxes. And so the real key is some of the microscopic design. So as one example, in like design for handling carbon black, it's so sticky that oftentimes any constriction in a pipe will just clog because it just sticks there and forms these little bridges over pipes. And so what you have to do is be really careful about like all the angles of those faces in your pipes. So like if you have acute angles, that's really bad, that'll clog. Whereas obtuse angles tend not to clog quite as much. And so you have to be really careful about at every point in the entire system, where do you have these potential clog points and how do you design those out?
Have you run into anything along the way that has been sort of a technical roadblock that you just didn't know, or a failure point where you're just like, I don't know how are we going to get around this?
Nothing quite that severe, thankfully. I mean, I could talk to you all day about the setbacks we've had. There are so many. As one example, we talked earlier about really high temperature materials and having to have those materials joined to one another. And so we have all these joints and interfaces, and at 1000 C, these things break, right? And this is hard to simulate because material properties in these kinds of regimes just aren't known. And if you misalign something by a millimeter, that puts a new stress on this piece and it'll crack, and then you have a leak. And it's really frustrating when you keep failing and failing and failing again and again. But I've come to kind of accept and embrace that that's often the inherent nature of doing something that's new and hard and meaningful in deep tech hardware like this. And R&D, unless you're incredibly lucky, is 95% or more like failure and iteration. And ultimately, it's my belief that the name of the game here is just fast and effective iterations to quickly learn what's going on and what's going to work and not work, and not deluding yourself into thinking that, hey, I'm going to spend 6 months designing the perfect system and have it work. You don't know. It's the first of its kind. It's probably going to fail. And so I think the name of the game for me and my technical leadership team is how can we iterate and learn as fast as humanly possible and make failure part of our culture, because we want our team to be able to enjoy that learning process and stay energized despite repeated failures on the way to all these solutions.
I love that. You're ramping up to sell your first units commercially, it sounds like. What kind of volumes are we talking about when you're at commercial scale? Are you making hundreds of units or thousands, or I'm just kind of curious what kind of volumes you're looking at?
Let me answer a slightly different question.
Sure, yeah.
Yeah, so a typical unit at commercial scale will ultimately produce order of magnitude about 1 ton per day of hydrogen. And you could think of this like a shipping container that shows up at some customer site and outputs the hydrogen from their natural gas meter effectively. And so when you think about the available market for that, it's enormous, right? Every factory that uses process heat, every building with an on-site generator that wants to decarbonize, any building that has a large boiler or furnace in the basement that runs on natural gas, these are all opportunities. So initially, our customers right now are getting kind of beta type pilot units. They're a little bit smaller. And so, there are early adopters, but part of the roadmap moving forward is designed for that scale up and getting to that commercial size.
I'm curious to hear from you because we talked a lot about kind of that sort of the 0 to 1 challenges of figuring out, how are we going to move this stuff? How are we going to seal it? How are we going to filter it? How are we going to manage all the high temperatures? I'm curious if you're getting a sense of what's harder, going from 0 to 1 or going from 1 to whatever volumes you're ramping up to.
Yes. Nothing's easy. One of the things that I've learned and come to really appreciate is that scientists often kind of poo-poo scale up in manufacturing. And I think that's a missed opportunity. There's real knowledge and real engineering and real challenges and real math and real design that goes into that scale up. And so I think as we think through that, one of the things that's kind of unique about what we're doing is, yeah, we're developing a chemical process. But when people typically think chemical process, they say, okay, our pilot plant is a $15 million dollar endeavor. And then we need $100 million to build our demo plan, and then $1 billion to build our commercial plan. And one of the nice benefits of the modular distributed approach is that the barrier to entry, both for us scaling up as well as scaling this thing and getting it into a customer's hands, is lower, right? So the bill of materials is like an order of magnitude lower than a typical chemical process pilot plant for these beta units. And Mothusi can comment on, I think, the robust customer demand that we're seeing. But one of the things that I'm really excited about is that the feedback from the market so far suggests that the modular approach lends itself really well to scaling where and when customers are excited and ready to start decarbonizing solutions, that start decarbonizing their operations. And so ultimately what that means is we're producing more of these things, right? So we're producing a lot of these shipping containers as opposed to one big plant. And that means that we basically get to tee up like a typical contract manufacturing operation that says, hey, go assemble 20 of these things for us. And then we get the benefit of the economy of scale. And we're pretty early stage, being super candid and transparent about this. There's still a question of exactly what is that manufacturing model? Is it contract manufacturer? Is it do it ourselves? Is it automate the whole thing? And a lot of that's going to come from what the market says they want, and in terms of scale and timeliness. And frankly, also which contract manufacturers could grow as fast as we could.
That makes a lot of sense. Have you had to change your team makeup as you're starting to get into that phase of development?
So I think a lot about this right now, actually. And the answer is yes. So Modern Electron is an R&D heavy company. And one of the things that we're seeing now is as we add more, I'd say like commercially oriented or like design oriented engineers, we're having a bit of a culture clash. And it's actually really interesting to watch because the good R&D scientists are the folks who are like constantly expanding the funnel of possibilities and generating learning and knowledge. Whereas the engineers are like, tell me what the requirements are, nail it down, decide, and I will design to that. And we see a lot of this kind of discussion like this. And I liken it, there's this management model of teams where it's like, okay, you have your forming, you're storming, you're norming, and then you're performing. And if you've been through like the management tutorials, you've probably seen this. And I think we're still like working our way through that. So I'll spare you the details so I don't embarrass my team. But part of what we've had to put in place as a management team are some kind of robust info sharing processes between R&D and engineering that allows these different mindsets to coexist and to share information usefully, but also helping people have a little bit more empathy for the folks in the opposite function, right? Because it just makes the communication easier. So there's a lot of work to do in terms of making sure these teams can scale a first of its kind technology and bring that out into the world. Yeah, you definitely need different types of people, but you have to figure out how to make them work together because ultimately both have to work hand in hand to make this a win.
And then eventually it's all got to be in that form factor and crystallized where you get it out at your customer location. And the same way that you're managing that dynamic between R&D and engineering, it's how do you manage that dynamic between R&D, engineering, and now you've got a customer out there. It's a fascinating space to be.
And is that a role you help to play, Mothusi, representing the needs of the customer in the development process?
Woohoo! I think that's probably the single most important thing that I do. It's a two-way street. We're early enough in the marketplace where we have some very sophisticated customers, but in understanding the use case and what needs to happen on both sides, you're constantly navigating and trying to pin down, okay, if we can deliver X, Y, and Z, what can you do with that? How much are you willing to pay for that? How long is it going to cost to do system integration? And does that become like a rate limiting step in our path? That's the brilliant part of being in early stage hardware space, is that it's not as easy as software where you can go back and rejigger and just regurgitate a new product like Max is talking about. Regurgitating on the hardware side takes years.
As a hardware engineer, I love talking about how much harder it is than software.
I think we're all biased on that front. But I also think that we can learn a lot, right? The rapid iterations and rapid learning cycles, like that applies to R&D too. It really also applies to kind of like customer learning and iteration between engineering and customer to kind of negotiate those requirements, right? And we've had to do quite a bit of that. And I personally love working alongside Mothusi and our customers and kind of at the interface between engineering and customers to say like, hey, customer, we can't really do this. Are you cool with this? And kind of going through that negotiation, right, to find a win-win solution. It's not always easy. And sometimes people say no. That's always part of the fun is how do you get creative and find that win-win and negotiate between competing requirements.
That's really interesting. And it's probably especially fun because you're providing something that doesn't exist today. So you're kind of in that, what is it? If Ford had asked people what they wanted, they would have said a faster horse. You're giving people something new that they wouldn't necessarily know how to ask for because it doesn't exist. So that customer requirements gathering journey is pretty interesting.
Totally. And part of the magic here is like, we do get to kind of paint a picture of what the future looks like. And part of it is also more traditional requirements gathering, but there's definitely a little bit of customer education because nobody's ever thought about solutions like this before. And so, some people who we talk to, I would say like, we tell them what we're doing and their eyes light up and they're like, oh, wow, this might change the game for me or my company. And other people, we have to drop a few more breadcrumbs along the way to help them see the potential future. And thinking about that future and what it is, like at steady state in like 10 years or something, and I'm not going to be foolish enough to give you a specific timeline at any real resolution, but like I want any of these customers who use a lot of natural gas to be able to come to us and say, hey, we're ready to decarbonize. And we'll show up a few weeks later or a couple months later with a shipping container, help you hook it up to your gas meter. And then within a few days after that, you're getting hydrogen that helps you make your beer or your steel or your copper or whatever in a way that's no longer emitting CO2.
And Max did say beer first. So let's make sure we've got our priorities straight.
Yeah. It's good to know what's important.
If I can just add another piece there, Max talks about like educating these potential customers. There's no question it is educating, but oftentimes it's like challenging them. It's challenging the assumptions that they have, challenging not only their understanding of what is today, but what is possible in the short term, in the long term. And we're creating these new pathway scenarios. It can be a really frustrating place to be, but it can also be probably the most rewarding space on the planet, where when their eyes light up and they get it, then there's no turning back.
Yeah, that's when you become really, really valuable to your customers, when you challenge them, you push them. You started talking about the future a little bit there, Max. I'm curious, are there other problems you might tackle on the roadmap or that you would put on the roadmap had you more time and resources to do so?
One holy grail in the hydrogen space that people haven't been able to figure out is how you store gaseous hydrogen at a reasonable energy density. And the state of the art in terms of hydrogen storage right now is if you have a hydrogen tank, I think about 5% of the overall weight of the storage system is hydrogen and 95% is the tank. These high strength but lightweight tanks are definitely a holy grail that I don't think anybody's figured out yet. Same with storage, right? How do you store hydrogen at really high energy density, but without having to use a ton of energy to compress it to 800 atmospheres of pressure or something like that? I think that's a really unsolved problem.
Because your customers won't have to store it. They'll use it as it's just on-demand hydrogen as they need it.
That's exactly right.
Yeah.
A
few last closing questions, and this is for you, Max. How optimistic or pessimistic are you about the future of our planet and why?
We have a lot of reason for both optimism and pessimism. And very candidly, I'm not sure I can make up my mind one way or the other. I see two really big challenges to addressing climate change at a global level. One that really keeps you up at night is that the majority of CO2 emissions are going to come from the developing world in the next 50 years. And that's concerning because these countries don't necessarily have, for instance, the infrastructure or frankly, the funds to be able to reduce CO2 in the way that Europe has kind of been the pathfinder on, and the US and Canada are fast followers on. And as one example of that, there's this horrifying reality, which is that the majority of CO2 emissions reduction from Europe in the last 10 years has actually come from industry moving overseas, not from actual changes to the way that we do things in terms of how we make things or burn fuels. And so I think this is a real challenge that we as a global kind of climate tech and climate change community need to think about, is how do we make our solutions available both in US and Europe, but also in the rest of the world. And the second challenge is that most clean tech solutions are still more expensive than traditional solutions. And this is what Bill Gates refers to as the green premium. And I like that term. It basically refers to how much more expensive the green solution is than business as usual. And what this means is that we either need to institute better incentives, either positive or negative, for clean tech that don't just drive dirty processes overseas, or we need to innovate, right, and find cost-effective solutions. But I also think that there's a lot of reason for optimism. And a big one that I'm seeing is that we're getting better and smarter and more educated about addressing emissions in non-traditional sectors. And people are coming to realize that, hey, the power grid is incredibly important to decarbonize that, but that's only 20% of our country's CO2 emissions. And we have agriculture, industry, transportation, and so on. And these things all contribute massive amounts of CO2. But what's really encouraging is that I'm seeing a ton of innovation in these other spaces, whereas 10 years ago, I would say most of it was only in the power generation sector.
Mothusi, who is one other person or company doing something to address climate change right now that's inspiring you?
Henrietta Moon and Christopher Carson's at Carboculture. I think carbon capture is a critical piece of the equation. They're doing some really disruptive work in distributed carbon capture, particularly around agricultural waste. And Christopher and I met years back at StartX, and we've cross-collaborated around fixing carbon. And I just really get inspired by the work that the technical team over there at Carboculture is doing.
Cool. I'll have to look them up. That is definitely a big problem. And it's amazing sort of the diversity of approaches people are taking. So I'm excited to see what they're up to. Thanks for giving them a shout out. Max, anyone you would add?
Yeah, so I'm really jazzed about what a company called Carbon Cure is working on. And they basically have a solution to do CO2 capture and reuse in cement production. So it turns out that when people make cement and concrete for buildings, it releases a lot of CO2. Multiple single-digit percents of our overall CO2 come from cement and concrete. And so these folks have a solution that's really cool. And they install this kind of modular unit on site at a cement plant and lower the carbon intensity of producing concrete. And so I think that is really cool. And Rob Niven and his team are incredible technologists and incredible product people as well, with the way they've been able to get like a really hard tech deployed in an industry that has been doing the same thing for literally a few thousand years and is characteristically or maybe stereotypically a little bit conservative. They've actually made some really impressive inroads and have started to make an actual real appreciable dent in CO2 emissions from that industry.
Awesome. I've read about that, but don't know much about it. So I'm going to have to look those guys up too. That'd be a fun episode to do. What advice do you have for someone not working in climate tech today who wants to do something to help?
So I have 3 pieces of advice, and I could probably go on all day about this. But first is related to what we were talking about before. The goal in climate tech should be to decarbonize affordably. It really shouldn't matter what fuel or energy source or industry people are looking at. And so to that point, there are lots of opportunities for getting involved in climate tech or climate change that don't relate to batteries, solar, and wind, right? And that's what gets most of the attention even still, is decarbonize the electricity grid. And we talked about concrete as one example. We've already talked about metals and steel and copper and buildings. And there are tons of challenging and important problems in other sectors and with other technologies. And I'd suggest people seek those out and don't go with the herd, because at this point, solar and wind and soon batteries are commodities. And so it's going to be hard to differentiate your offerings if you're doing real tech innovation. Second thing is that a lot of friends ask me how they can get involved in climate change and climate tech, and a lot of them come from the software world. It's pretty timely. I don't know when this will be released, but yesterday Elon Musk had this funny tweet, which is something like, take materials science 101, you won't regret it. And that applies in this context, right? Because CO2 is a molecule and energy and climate change exists in the world of atoms, not bits. And maybe I'm preaching to the choir here, a bunch of hardware engineers, but lots of Silicon Valley people say software is going to eat the world, and they're really not wrong. I mean, look at what's come out of Silicon Valley in terms of value and improvements to people's lives. But software alone can't solve climate change. It has to pair with hardware. So if you're going to get involved, make sure you understand how to do some of the basics of how the hardware in your sector works, and make sure you know how to do like back of the envelope calculations through important units like mass, energy, and power. And a lot of people don't even have the kind of basic like back of the envelope skills to do that. So I think that's a must have if you're going to get involved in this industry. And then I think the last thing to emphasize is that it's not just the technology or the hardware that matters toward addressing climate change. And here's where I'm going to annoy some of the hardware engineer listeners. So I touched earlier on cost-effective solutions, right? Energy and industrial production are some of the biggest industries on the planet. And the companies in these industries or these sectors, have a mandate to return value to shareholders and earn a respectable profit. And I respect that a lot. So what that means, though, is that for any clean tech solution to actually scale and make the real CO2 impact that we want it to have, it has to be cost effective and it has to be convenient. And what that means is we need the technologists, the hardware engineers like me and you, Dylan, working really closely with the financiers, the manufacturing and operations experts, like we talked about. That's its own really hard challenge, is getting things at scale and cost effective. Industrial designers, salespeople, policymakers. And I see this attitude often in scientists, which is, well, I worry about the scientists and the engineers do their thing and the MBAs do the other stuff. And vice versa from the business folks and the policy folks and the design folks. And I even see that silo attitude sometimes between engineers and scientists in the same company, like what we talked about earlier. But that's a missed opportunity. And some of the most effective business, policy, and technology folks I've met are at least able to tango with the basics in the other domains. Because ultimately, if you understand what the other domains need and their constraints and their goals, it helps you design better, effective solutions in your own domain. And so if we can learn to speak each other's languages, we can build better, more cost-effective and practical solutions that actually scale and actually work with regulation, and the customers will actually buy. And that's really important, but it takes work. And yes, that means you have to go read a book on the weekend or come up to speed or get out of your silo and have a conversation and get curious. But the hard truth is all of these conditions are binary. The tech has to work and the business has to work. Otherwise, we're not going to get climate tech to the scale that we need to make the impact on climate change that we need it to.
I love it. It's really practical advice. And I particularly like that you're calling out that it's very multidisciplinary and everybody's got to work together, but kind of regardless of your background, there's probably a place for you to play. So I appreciate that. Thank you. Mothusi, how about you?
In my mind, in climate tech, as in a lot of other startups, there's the chunk of work that's the idea, there's the R&D, and there's the implementation. And I think a lot of people who are interested in climate tech get hung up on the idea that, if I don't have the idea, then I can't do it. But at the end of the day, probably the hardest part, once you get past the science, is the actual, to Max's point, it's got to scale, it's got to be cost effective. How do you implement it? How do you get heavy industry? How do you get big established sectors that have a set operating model to start thinking differently? And I think that the big challenges, number one, are don't boil the ocean. We need to understand that decarbonization is a big space, but you're not going to make any progress if you don't pick a single project and dig and dive in. So find a problem and work on that one single problem. But then this doesn't have to be in the idea and R&D phase too, that there are and need to be subject matter experts in implementation. That means that you don't have to be at a startup to do climate tech. I mean, probably the biggest opportunities for large-scale decarbonization are in big corporations. Like, we need advocates on the inside. We need thinkers challenging the kind of status quo on the inside. That it's bigger than just the startup universe. I think a lot of people think that if I'm going to do something in climate tech, I have to be in Silicon Valley. It doesn't matter where you are, and it doesn't matter what company you're working in. I think it's the state of mind and really a willingness to lean in.
That's a really good point, and easy to forget that kind of sometimes being in the Silicon Valley bubble. Thank you. Well, Max and Mothusi, that was a really fun conversation. I really appreciate all your time and everything you're doing. I'm excited to see where Modern Electron goes. I'll be cheering from the sidelines. Thanks, guys.
Thanks so much, Dylan. Yeah, we're excited about what we're doing, and we appreciate the opportunity to chat with you and your listeners about what we're up to.
Yeah, thanks for having us.
Hardware to Save a Planet is brought to you by Synapse. To find out more about us and how we develop hardware solutions for the world's most ambitious companies, head to synapse.com. And then make sure to search for Hardware to Save a Planet in Apple Podcasts, Spotify, and Google Podcasts, or anywhere you like to listen. Make sure to click subscribe so you don't miss any future episodes. On behalf of the team here at Synapse, thanks for listening.